today's video, where we shall be looking at our topic, which is nuclear processes. And as usual, your teacher is Teacher Heber William. And please, before you go any further, don't forget to subscribe and like this channel, so that you can always be alerted the moment we put some new lessons. And in case you want to reach out to us, please, you can get us on the WhatsApp number 751 40 71 58. You'll be able to get us. Okay, let's dive into our today's work. We shall be looking at majorly radioactivity. We shall talk about half-life, and then nuclear processes, which is fusion and fission. Then we shall look at general applications of nuclear energy. It's a very interesting story, more so considering the current events happening in the world, looking at the development of science and the energy, the nuclear energy. So I hope you learn a thing or two. Let's go straight to what radioactivity is. Basically, when we say radioactivity, I'd like to remind you from your previous topic, from the topic of atomic structure. You looked at what an atom is, you looked at the components of the atom or the particles we find within an atom. You saw that you have that tiny part within an atom which is known as a nucleus, and in that nucleus you find there some particles which are protons and neutrons. And you said, you discovered that according to different atomic models, more so the Rutherford atomic model, you looked at that electrons are not within the nucleus but they are outside the nucleus. So here we are going to be majorly focusing or looking at the nucleus part of the atom. That's why even the topic is called the nuclear processes. So when we define what radioactivity is, we are basically looking at when a nucleus is heavy and then it starts breaking up uncontrollably. And when it breaks up uncontrollably, of course, since it is a nucleus, and what makes up a nucleus? Protons and neutrons. Good. So when it breaks up and it is releasing some particles, some of those particles may be neutrons, some of the particles may be protons combined with neutrons, meaning forming another nucleus, or it may even, as in the process of breaking, it can just release some energy, or even it may cause an electron to move out of that atom, out of its atom. So that's what we call radioactivity. So if you want to define it in simple terms, it is the spontaneous disintegration of a heavy and stable nucleus to form a stable nucleus, but it is always accompanied by release of radiations. So like I've just told you, these radiations, or what we are calling radiations, are basically the alpha particles, the beta particles, and the gamma rays. That's what we call the alpha particles, the beta particles, and then the gamma radiations. Those are the radiations we are talking about. And now, if an element, hope when I say an element you remember it, an element, it can be carbon, an element, it can be, let's say, magnesium, it can be sodium. If an element emits those radiations, any of these three radiations, then we say that element is undergoing radioactive decay, and therefore we term it as a radioactive element. Okay, so that's about how elements or a nucleus can decay, and that process of decaying is what we call radioactivity. Now it is spontaneous because you cannot control it. You cannot say any physical factor will control it. That's why it is spontaneous. Like you can't predict which atom or which particle will be decaying, or which nucleus will be decaying at any given instant. That's why radioactivity is unpredictable and it is spontaneous. Let's look at what we call activity. Now, activity, it's like if I would say you are in your class and every second two people are moving out. Every second two people are moving out. So that is what we shall say the activity of your class is two people per second. Two people are moving out per second. So when we are looking at an element or a nucleus which is decaying, then we are looking at the number of particles which are being emitted every second. These particles, remember we said the radiations, they may be alpha, they may be beta, it may be gamma rays. That's what we call activity. And if you move on to advanced physics, you realize that this activity or the number of particles moving out depend on the number of particles present. Okay, like let's say if you have a class of 50 students, and you may find that every time, in case of let's say there is an exciting event outside, students are rushing out, you may find that you're having 10 students passing through the door every second. But if a class is of let's say 10 students, then you may find because they are few, every second you might find you're having only like 3 students moving out every second. So in advanced physics, you'll discover that the number of emissions depend on the number of particles originally available, meaning when the particles are many, then more particles are emitted. When the particles start reducing, the particles being emitted start also reducing. Let's look at the properties of these radiations. Now, I have just combined all the three to make them in summary. Like we said, we have the alpha, we have the beta, and then we have the gamma rays. First of all, the alpha particles, these are the helium atom. Now that's sounding crazy, right? Because we said it is a nucleus that is decaying. Okay, if I have a nucleus that is decaying, and when it was breaking down, it emitted 2 protons and 2 neutrons. Those 2 protons and 2 neutrons, meaning they moved together as if they formed one nucleus. They formed a new nucleus. Now you realize an element which has 2 protons and 2 neutrons, that element is known as helium. So that particle shall be calling it the alpha particle. So an alpha particle in actual sense is a helium atom or helium nucleus. Okay. Then the beta particles, this is a high energy electron. If a nucleus was decaying and then an energetic electron was ejected, it was moving, that electron, we call it the beta particle. That is the particle we call a beta particle. Then gamma rays, these are electromagnetic radiations of the shortest wavelength. Remember, if you recall from your electromagnetic spectrum, you saw the different wavelengths for the different radiations. You realized that the gamma rays have the shortest wavelength, followed by X-rays, followed by ultraviolet radiation, then the visible light that we see, you go on decreasing like that, infrared, microwaves, and so on, radio waves, etc. So they go on, the wavelength goes on reducing. So gamma rays are part of the electromagnetic. So if I have a nucleus which is breaking up, then it has emitted a radiation which is of shortest wavelength. That radiation is a gamma radiation. Now, since we know that the alpha particle is the nucleus of a helium atom, then it means in the nucleus we find there protons and neutrons. So it has 2 protons, and protons carry which charge? Positive, correct. So alpha particle is positively charged, or alpha particles are positively charged, and they have a charge of positive 2 because it is having 2 protons. Now if each proton is carrying 1 positive charge, so it is a positive 2. Whereas for the beta particle, since it is an electron, and we know electrons carry a negative charge, so beta particles are negatively charged. Gamma rays are neutral in nature because they neither have protons nor do they have electrons. Now, because these particles are charged, alpha particles and beta particles, meaning if you bring them between let's say electric field, you put them between two plates, one being positive charged and another one being negative charged, they will be attracted by either. If they are alpha particles, they will be attracted by which terminal, by which plate? It will be attracted by the negative one, because the particles are positively charged, so they will be attracted to negative. Whereas the beta, they will be attracted by the positive plate, since for them they are negatively charged. So the gamma rays are not deflected, they are not attracted by any either magnetic or electric fields, because they have no charge. Now, due to the high charge, remember alpha particles have a positive charge, positive 2, and beta particles have a negative 1. So positive 2 is a very big charge, meaning when they pass through the air, they can easily ionize the air. Remember what ionizing means: breaking the air into two charges, positive and negative. So as the alpha particles pass through air or gas molecules, they will cause the gas to have the two poles, or the two ions, the positive ions and the negative ions. Why? Because they have a high positive charge. Beta particle can also neutralize the charge, but not as much as the alpha particle, since for it has a lower charge, which is of negative 1. Gamma rays, they can ionize, but at a very small extent. Remember, gamma rays are not charged. So when we look at the penetrating power, alpha particles have a very low penetrating power. In other words, they can be stopped by a piece of paper, because they are very heavy. They have a mass number of 4. They are heavy. So it's like anything that is heavy cannot easily go deep. Okay? It cannot penetrate so much compared to something small. So when you look at the beta particles, for them they are a bit light, and it is an electron. It has a mass number of 0. So it can easily penetrate, and it can be stopped by aluminium foil. And when we look at gamma rays, for them they are very highly penetrative. Remember, they have a very short wavelength, they are not heavy, they have no mass number, so they can easily penetrate any matter, and they can only be stopped by very dense piece of matter, like let's say lead shield, concrete, etc. Then because these alpha particles are heavy, it means that they cannot move very far. It's like if I tell any two people here, one who is very big and another one who is very tiny, I tell them to run, you realize that the smaller one might run faster than the bigger one. So alpha particles are very big, they are heavy, they don't go very far if you push them in air, so they have a low range in air. Whereas beta particles, they have a longer range, and the gamma rays have the longest range because they are very, very light. So that is the simple overview of how these particles or these radiations are, by nature, by characteristics, by how they are affected by the surrounding. So that gives us the properties of the radiations. Now let's look at this decays in the form of equations. For alpha decay, we've said that if I have a nucleus which is having a mass number of A and an atomic number of Z, and it undergoes an alpha decay. Remember, an alpha decay meaning it emits 2 protons and 2 neutrons, meaning the new part of the nucleus that remains will have its mass number reduced by 4. Why? Because it lost 2 protons and 2 neutrons, meaning it reduced by 4. So the atomic number will also reduce by 2, because it lost 2 protons. Remember, atomic number is the number of protons in the nucleus. Take an example. If we have like uranium 238, it has a mass number of 238 and an atomic number of 92, and it undergoes an alpha decay. It decays by emitting an alpha particle. This uranium here, meaning its mass number is going to reduce by 4, right? So it will remain as 234. And the atomic number will reduce by what? By 2. So it will remain with 90. So if uranium has lost four of its mass number and 2 of its atomic number, then it means it will now have become a new element which is now called thorium. So that is how the decay is happening, meaning even thorium can as well undergo the alpha decay and it becomes a new element, and the process continues. That is what we call the radioactive decay. So when we look for a beta decay, if it is an element, if it is an atom, and it is decaying, undergoing a beta decay, meaning it is going to lose an electron. Now, if it loses an electron, remember the number of electrons have to always be equal to the number of protons. And to remain the stability, remember an electron has a mass number of 0. So if this atom had a mass number A, meaning its mass number has not changed, but its atomic number, because we lost an electron, we did not lose a proton. Now when that electron is lost, but the protons increase, it's like because the protons now are remaining more than the number of electrons that we have now in the atom. So the atomic number will increase by 1. So in other words, when we look at the left hand side and the right hand side, they have to remain balanced. The mass number on the left hand side has to be equal to the mass number on the right hand side. Total atomic number on the left hand side should be equal to total atomic number on the right hand side. Like what we have and what we had earlier and what we have now should give us the same answer. So that's why you see that the atomic number has been increased, because if we add this atomic number with this atomic number, you realize we shall go back to 0. That's how a beta decay occurs. You can as well look at an example. If we have sodium, which is sodium 2411, and it decays by undergoing a beta decay, it will end up turning into magnesium. Why? Because its atomic number will increase to 12, and yet its mass number remained 24. And we know the atom which has a mass number of 24 and atomic number 12, that is magnesium. So that's how a beta decay occurs. Now for gamma decay, we said, remember, gamma is just energy, does not have mass number, nor does it have atomic number. So if it decays, an element decays by undergoing a gamma decay, its atomic number will remain the same, its mass number will also remain the same. Mass number A will remain the same, atomic number Z will remain the same, because gamma was just a radiation. Take an example. If we can have barium, for example, can decay by undergoing a gamma decay. It will change. It had a mass number of 137 and 56. It will just emit a radiation, but it still remains the same element. So that is what we call the gamma decay. And this summarizes for you how the different elements can decay and by undergoing different emissions. Even sometimes a given element may decay by emitting more than one particle. It can decay by emitting an alpha particle and a beta particle. You should be able to as well balance such an equation in case it comes up. You can even practice it. Let's look at now the applications of radioactivity. Where do they get used in real life? What is the importance? How are they useful? Now, generally, the uses of radioactivity, they are in 3 major areas. There is a medical sector, there is industrial sector, there is agriculture, there is defense. So they are those areas, but we have just generalized here. I know you can even do more research and then you get more about them. One use is gauge control. For example, when they are making like iron sheets, they are making like sheets of paper, they can use beta particles to control the thickness. Can use beta particles to control the thickness of like a piece of paper, because remember, beta particle can go through a piece of paper. So they can get to see if the thickness is changing, then it means the number of beta particles going through will also change, and then the workers or the engineers can be able to adjust the thickness to know that the thickness of the paper is now changing, it is not the same. Radioactive tracers, you can inject them, like let's say in a pipe. Is like, let's say national water is transporting water, they want to know if the water is leaking anywhere. They, for example, if they inject in two particles, alpha particles, they expect at the end of the pipe to receive two particles. Now if they receive one yet they injected in two, then it means that somewhere there is water leaking. You see, that's what we call the radioactive tracers. They can even be used in checking how animal plants are taking in fertilizers. They want to see if they inject some radiations in the fertilizer and they test in the plant how many particles are found in the plant. They'll get to know this type of plant or this type of fertilizer is being absorbed very well, or this one is not being absorbed very well. Radiotherapy, like let's say using gamma rays to treat cancer. Remember I said gamma rays are almost as useful or they do the same work as x-rays. You looked at x-rays and atomic structure when you are looking at a thermionic emission. So gamma rays can be used to kill the cancer cells, and when they burn the cancer cells, it means now the cancer cells will no longer be growing, and then the person can be healed of cancer. That is what we call radiotherapy. And if you see the word radio, it is coming from radioactive, but there is therapy, which means medicine. So meaning we're using radioactive therapy, which are the radiation therapy. We're using gamma rays, which is a radiation. They can as well be used to sterilize equipment. Remember I told you to kill the germs, to disinfect, that is sterilization. They can be used in archaeological studies, like you can approximate the date of the, let's say, the remains of human beings, the remains of plants. You can study the structures using the radiation that for example, if a human, if all living things when they are alive they take in carbon, but the day you die, that is the day your body will stop taking in carbon. Instead, the carbon you have starts decaying. Now we are going to look at the decay now, the half-life. So when it is decaying, we can approximate to know for how long has this individual, this thing has been dead, by looking at how much carbon has remained in. We will look at it and see we are going to look at it in some examples ahead. So that is all archaeological studies. The radiation can as well be used in energy production in nuclear reactors. We are going to look at that, how energy is produced, most especially electricity or even heat, how it is produced. And the radiation or radioactivity is as well used in manufacture of weapons. I don't know if you've ever heard about nuclear bombs. Good. So that is still under radioactivity. Let's look at now, we've seen the uses, we've seen the applications, the importances, but it comes with some dangers. So some of the hazards and the precautions you need to take. Hazard number one is radiation is very, very dangerous. Never play with anything that is radioactive. Don't play with anything that is radioactive, because one, it can burn you, the radiation, because some of them they are very hot, like gamma rays, they can burn you. Remember I said they burn cancer cells. Now if cancer cells are not there, then they will burn your normal cells or even your skin. They can cause the redness and the sore on the skin. Leukemia, they can cause blood cancer. Remember when you allow the radiation to enter your blood, like let's say alpha particles or gamma rays or beta particles, they enter your blood, they will change the cells of the blood, and once the cells change, that is what is known as cancer. If a cell is not normal, then that is what is called cancer. So if they enter in the blood, then you'll have blood cancer, which is known as leukemia. So don't play around with radioactive substances. They can cause sterility, like let's say inability to produce, like they can burn your eggs. If you're a man or a woman, you will end up losing the reproductive cells, let's say the sperms or the ovaries, and then you find in the long run you may not be able to produce children. So that is inability to reproduce. They can cause blindness if you look through them. They can cause your body not to fight diseases very well because they damage the white blood cells. They can as well cause the mutation, like causing your genes to change. You find your skin is supposed to be black, and because the radiations are changing the genes in you, the DNA, I know you understand it better in biology, that nucleic acid which is responsible for carrying certain traits, that you're supposed to be brown or to be black, to have a black hair, to have maybe 2 arms, to have 5 fingers. That is all DNA. So once the radiations enter there, they start tampering with the DNA, then you'll find that a person's appearance is changing. That is what we call genetic mutation. So please take serious precaution when handling the radioactive substances, and one of them should be never touch it with bare hands. Use forceps or pair of tongs. I know you've ever seen those in the laboratory. If you've never seen them, then it is like using something which is not using something to hold, not using your own hands. Then avoid eating or drinking around a radioactive source. The radioactive sources must be kept in lead boxes. Lead, is a dense element. It is a dense metal, so it can absorb the radiations. And wash your hands every time when you get exposed to radiations, so that you don't take in any particle that may be on your hands, or any radioactive substance that may be remaining on your hands, because it will cause you problems. Cover any cut on your body if you have any cut, to prevent radiation from entering your blood. Remember, we said it can cause you leukemia. Then you wear gloves and lead coats if you're going to do experiments or to tamper with radioactive substances. And when you're carrying out an experiment, please avoid directing it to people. Don't direct radioactive materials to people. That's about radioactivity. So let's look at what we call half-life. Now, half-life, when we say half-life, like you hear the word half-life, what does it mean in simple terms? Just half of your life. It's interesting. So by definition, here we are talking about the time it takes for a radioactive substance to decay to half of its original either mass or activity. Remember, I defined what activity is. If originally you were 100 kilograms, the time it takes for you to become 50 kilograms, that's what we call half-life. If originally you were emitting 20 particles per second, the time it will take for you to start emitting 10 particles per second, that is what we call half-life. So the half-life can be in seconds, it can be in minutes, it can be in hours, days, weeks, months, years, centuries, etc. Any unit of time can be used to mean half-life. Take an example. Like I've just said, if a body is 100 kilograms and it starts decaying, the time it will take to reach 50 kilograms, remember originally it was 100, to decay to 50 kilograms, meaning it has now decayed to half of its original mass. That is what we call the half-life, and we symbolize it with T, which is time, then the subscript half, which means T a half, which we call the half-life. Therefore, if we say, if for example its half-life is 5 months, it means it will take 5 months for it to decay from 100 kilograms to 50 kilograms. Now, the current mass will be 50, meaning for it to decay from 50 to 25, it will again take 5 months, because that is the time it takes to decay to half of the original mass. So if it was 150, now 50 becomes the original now. By the time it decays from 50 to 25, it will take 5 months. That is another half-life. Then from 25 to 12.5, which is a half of 25, still 5 months. It goes on like that. It will again take 5 months to decay from 12.5 to around 6.25, which is a half of this, like that. So if I'm to ask you in simple terms, how many half-lives does it take to decay from 100 kilogram to 12.5 kilograms? You realize it will take the first half-life from 100 to 50, the second half-life from 50 to 25, then the third half-life from 25 to 12.5, meaning it takes 3 half-lives to decay from 100 to 12.5. So now if each half-life is 5 months, the total time it will have taken is what? Good. It will be 15 months, because the first half-life 5 plus the second 5, 10 plus the third 5, 15. Okay, yeah. So let's look at an example. We first see how we can determine half-life. In case I have an element and I don't know how to determine its half-life, I don't know its half-life, so then how can we determine it? We have two ways how we can determine it, that is using table format or using graph. Let's first examine how we can use a table. Consider, let's say, something like this. We go on breaking it down like this. If this is the mass remaining, I will be taking it against time. Originally, if I have M original, meaning the original mass, M naught, original mass, that is the mass I'm having before time starts counting. Now, when the time runs to what we call the half-life, one half-life, then the mass remaining will be a half of the original mass. And I get another half-life, meaning the total time I'm having what now? 2 half-lives now. The mass I'll be remaining with will be what? Will be a half of this half, which becomes a quarter. Then I go on breaking. For the third half-life, I'll be having a half of this a quarter here, which will be 1/8. That is after 3 half-lives, and so on until I can be able to determine the half-life. Now, take an example here. If I had 80 kilograms that decayed to 10 kilograms in 6 days, then how can I determine the half-life? 80, I had 80 when the time was 0. It decayed to 40 after 1 half-life, isn't it? Yes. Then it decayed now to what? From 40 to what? To 20. After how many half-lives? 2 half-lives. It decayed then from 20 to 10. After how many half-lives? 3 half-lives. Good. So it means if it decayed from 80 to 10 after 3 half-lives, it means, and they've told us that for it decayed from 80 to 10 kilograms in 6 days, meaning 3 half-lives are equivalent to what? Are equivalent to 6 days. Now, each half-life is what now? You can tell me. Very good. It will be 2 days. So the half-life will be 2 days because you've divided by 3. Okay? So that's how you can determine the half-life of a substance using the table format. Take this example. The society got a pipe leakage of a radioactive substance that contaminated the water source for the villagers. When the water sample was taken to the laboratory for testing, it was found that the activity was 250 counts per second. The scientists advised the society that they have to wait until the count rate is below 8 counts per second before using the water again. Now, task. Advise the society after how long should they wait before using the water again if the half-life of the leaking radioactive substance is 2 days. Now, I don't know if you're getting the idea now. This is the original count rate that they had, but they are saying that they have to wait until the count rate is here. Now, they don't know when will it be, but they have told us that this substance has a half-life of 2 days. Now, as a scientist, can you now manage to break down this, to go on breaking down this by following half-life after how this half-life, what will be the count rate after this, until you get to determine after how many days will the water be safe. Okay, let's look at it. Let's see now. This is our count rate. We want to see our count rate per second, then the time. We know the count rate originally was 250 when the time was 0. Then the count rate became 125. It decayed to half. That takes how many days? Good, it takes one half-life. So that meaning those are 2 days. Then it will decay from 125. What is half of 125? Get your calculators. Half of 125 is 62.5. Good. So that, how long will it take to decay from 256 to 250 to 62.5? That will be 2 half-lives, and 2 half-lives will be equivalent to 4 days. Good. Then it will decay from 62.5 to what? To 31.25. Correct. After how many half-lives? 3. Good. 3 half-lives are equivalent to 6 days. Then from 31.25 to what? To 15. After how many half-lives? 4 half-lives, which are 8 days. From 15.625 to 7.8125, which is how many half-lives? 5 half-lives, which are 10 days. Let's not forget, they told us that this water will be safe. They have to wait until when the count rate is below 8. That's what they told us. Now we see that here the count rate is 7.8, meaning which is less than 8. We see that we get this count rate after a total time of 5 half-lives, which is equivalent to 10 days. So therefore, the society should wait after 10 days to start using the water again. Okay, that's how you can advise, how you can determine the half-life, or how you can use the half-life given to address a certain challenge or to approximate the time taken or needed. Let's look now how we can determine the half-life using the graphical method. Here we plot several values. Let's say the count rates after a given time interval, or the mass after a given time interval. And when we plot it, we get a graph which appears like this. Like originally, you may be having here an 80. Maybe after 2 days, you have a certain value. After 3 days, you have a certain value. After 5 days, you have a certain value. When you plot them, you have a curve which flows down like this. That curve. Now, you can be able to approximate from this curve what the half-life is. Remember, we said half-life, the time it will take for the mass to move from where it was before when the time was 0 to when the mass becomes half. So if it was 80, you just come here and see where is 40. Then you'll see 40 corresponds to what time. That time will be the half-life. Let's not waste time there. We just look at an example. For instance, we're saying if we had, let's say this is the curve we had, if we plotted our values and this is the curve we got, we see originally when the time was still 0 days, we see the count rate was 80. Now we want to see what is the half-life, or what was the time by the time the count rate became 40. We see when the count rate is 40, the time is 2 days. That is after 2 days. So implying that the half-life from that graph is 2 days, because we see at 80 time was 0. So by the time it decayed from 80 to reach 40, when we move from 40 and we reach the curve, then we read here down what the time is. We see it is 2 days. So that means that the half-life is 2 days. Let's look at an example. During mining activity in Mubende, a rare mineral was discovered, but the miners were warned that the mineral was radioactive and hence could cause health problems to them if they continued exposed to it. When scientists conducted a study on the mineral, the following results were obtained. And what are the results? They obtained the results that the count rates they were capturing after a given time. Before they started counting the time, the count rate was 800. After 4 minutes, the count rate was 520. After 8 minutes, the count rate was 345. After 12 minutes, this was the count rate. After 16 was 145. What is the task? As one of the scientists, determine the half-life of this substance. And then, if the radiation is said to be safe when the count rate is 200 and below, for how long should the miners stay away from the mineral every time they find it? Like every time they find it, how they should stay away from it for how long so that they consider it safe for them to continue working. So let's look at it. Like I said, when you have such information, all we need to do is to first have our graph. Let's first have our values there. So we plot our graph and we see how that graph can look like. We shall have here our count rate vertically, and horizontally we have our time, which is in minutes. So we know when the count rate was 800, the time was 0. When the count rate was 520, the time was 4. We plot. When the count rate was 345 should be around there. The count rate was 8. When the count rate was 225 should be around 25 here. We plot it against 12. When the count rate was 145 should be around the 40 thing, the 40 line here. The time was supposed to be 16. Sorry, I did not plot it well. It is supposed to be 16. Okay, let's say it is 18. Then now we want to determine the half-life. Like we said, we need to see what is the time for when it decayed from 800 to 400, because that is what we shall see half-life. So from 800 to 400, meaning it will have taken the time equivalent to half-life. So when we extrapolate, we move around there to the graph and we take the reading here down. We see, remember, each line is what? Is around a 2, because from here 6 to 8 you're having 10 small lines. Each line is what? Because here is 2, each line is 0.2, right? So we see that it is around 6 point, because it is in the second line, small line, it is around 6.4, depending on what you get. So we realize that from our graph the half-life is 6.4 minutes. So that is the half-life of the substance. And the other question they had asked, if the radiation is considered to be safe when the count rate is 200, after how long should the miners wait? We see that for the count rate to reach 200, from this graph we see the reading is supposed to be 13, isn't it? 12, 14, the meaning in between here is 13. So we see that the time is 13 minutes. So meaning every time they find the mineral, they should stay away from it for 13 minutes, because at 200 it will take 13 minutes for the radiation to drop to 200 counts. So therefore at 200 counts, the minutes or the time is supposed to be 13 minutes. So meaning every time the miners find this mineral, they should stay away from it for 13 minutes. I will first pause here. You can catch up the continuation of this lesson in the next video, or which is going to be labeled as part 2, so that you continue from there.